of detergent. Okay, so just remember that the detergent molecule is a rather schizophrenic molecule, we say. Okay, so it has two parts. So it has a hydrophilic head, like this part in blue, and a hydrophobic tail. Okay, so in the exam they will ask you what will happen if the tail is too long or if the tail is too short. Okay, so this is what I'm going to put down at the bottom of the page, or maybe on the side of the page here. So explain why is it not ideal for the hydrophobic tail to be too long or too short. So this end, we call it the hydrophobic tail. We don't want it to be too long or too short. Okay? So explain why is it not ideal for the hydrophobic tail to be too long or too short. So if it is too long, it will be too oil soluble and too water insoluble. Yeah, and you will see something like this. This is the oil dirt. If it is too long, then the hydrophobic tail it will stick out of the oil droplets, and it will make the whole thing not water soluble. So remember, for the whole thing to be water soluble, you want the head to interact with water. You don't want the tail to interact with water. But if the tail is exposed, it is too long, you see. So long that it sticks out of the oil molecule, it will be forced to interact with water, which makes it not very soluble. And then we also do not want the detergent molecule, the tail, to be too short. If it is too short, it will not be oil soluble enough. Okay, and so meaning that it will not be able to clean and remove or dissolve the oil as effectively. So put down what will happen if it's too long. So if it's too long, if it's too long, if it's too long, then it will be not water soluble enough. So that it cannot be carried by water easily. And so after you rinse the dish with water, some of the dirt remains because it is not water soluble enough. It cannot carry away the oil as effectively. And if it is too short, so it is not liquid soluble enough. So it will not be liquid soluble enough. So either way, it is not a very good cleaning agent. Okay, yeah, just remember that it has to be an optimum length. And then, let's continue with the second half. Okay, it's the last type of important organic chemical called the nylons. Okay, and the polyester. So any question on detergent first? Yeah, no, just know that it has two properties. Okay, it has an emulsifying property, and it can disperse oil in water in a stable emulsion. That's what emulsifying means. The second property is its surfacting property, the ability to reduce surface tension. To make the water hold onto one another less tightly, and this will help improve the cleaning property of water. And finally, here we have the remaining organic molecules. So which is the polyamides and polyester. So let's do a very, very quick review on the organic compound. Okay, we did some time ago the discussion on. What are amide group? What kind of atoms do you see in an amide group and an ester group? What are the atoms? NH. Yes, CONH. Well, just CON, right? Con, right? Remember con. So can you draw the amide and ester bonds? So we call that amides. They have the con group. Okay, so draw C double bond O. The connection has to be right. C double bonded to O, and then it's also singly bonded to N. Okay, but whether this N is attached to H's or alkyl group determines whether they are substituted or unsubstituted, we say. And then we have the ester. So ester have the cool group. So this is the COO. Yeah, just remember con and remember the cool. Okay, so the cool. So one is ester, one is amide. So in this chapter we look at polyester and polyamide. So So I'm sure you have learned something called polyalkene before, right? Remember polyethylene, polypropylene, polystyrene. So poly, the term poly tells you that they are polymers. Okay, so they are very long chain molecules. So indicates that they are long chain molecules called polymer. So long chain molecules called polymers. And we'll look at how polyalkenes are formed. So below, let me do a very quick summary on the types of polymer you have learned this far in DSE. So types of polymer. We have what we call the addition polymer. Can you tell me what are the characteristics of the monomers that make up addition polymer? What do the monomers have in common? CC double bond. That's what makes addition polymer. Addition polymer. So write down the two classes of polymer. So polymers can be either on the left, addition polymer, which are always formed by alkenes. And now add to your collection a second class of polymer. They are the condensation. I'll explain that in a second, the term condensation. But this should not be a new term to you. You have learned this in esterification. Esterification is a type of condensation, as it removes water when it joins two molecules together. So addition polymer means the joining of monomers to form polymer without eliminating anything. So that's what the term addition means. When you add stuff together, you don't remove things. Because if you remove things, you will have point subtraction. Okay, that's polymer. So you didn't point subtraction polymer. You call it addition polymer because you're just joining monomers to form polymers without elimination of small molecules. Okay, such small molecules as H2O or HCl. So condensation polymer, it will be the other type. So you know it's not black. If it's not black, then it will be white. Okay, so in chemistry, if it is not addition polymer, it will be condensation polymer. Okay, the class of polymer. So we can copy this definition on the side and change this word to with. So you see, one has no elimination of small molecule. One has. That's what condensation means. So maybe you can highlight this term. Condensation really just means the removal. Yeah, so the joining of two things with removal of H2O and HCl. And let's look at what makes addition polymer and condensation polymer. I mean the monomers. Okay, you know polymers are made of monomers. Okay, so you can draw this very simple diagram on top. Both types of polymers, they are made from the same type of building blocks. So I think you have all seen these Lego blocks before. So if you connect many of these Lego blocks together, you get a very, very long chain, okay, of molecules. So you can liken this to the monomer. So this is the monomer. Right, yeah, so this is the monomer. We just started the discussion on condensation polymerization. So this is the monomer. When you have n of these monomers coming together, we'll get a long chain molecule, known as the polymer. But depending on how the polymer is formed, whether there is elimination of small molecule or whether there's no elimination, we can call it addition or condensation polymer. So allow me to copy this. You don't have to copy this. If you have copied this definition, you don't have to copy this diagram anymore. There is nothing removed in the process. You see, nothing comes out. You just keep on adding things together. But when you do condensation polymerization, a lot of molecules of H2O or HCl, they will come out as the monomers join. So whether or not H2O or HCl is eliminated, it determines which type of polymerization you have. So the next standout feature of the monomers of addition polymers and condensation polymer, write them down now. The monomers here, what characteristics do they have? They are all alkene based, always. Okay, so all alkene based, meaning they all have the CC double bond. So all alkene based with CC double bond. This is a hallmark feature, okay, of the monomers in addition polymer. And then we have for condensation polymer. The monomers of condensation polymerization, they are often what we call diol. Do you remember diol? Diol means what? Things with two OH group, diol. They can be diol and dicarboxylic acid, okay, or dicarboxylic acid and diamine. So diamine and dicarboxylic acid. So if you know what carboxylic acid means, I'm sure you know what dicarboxylic acid means. They are things with two COOH groups. We'll get to that shortly. But can you draw the functional group for me now? So you have CC double bond, which is the functional group of alkene. You have OH group, which is the functional group of alcohol. You have so you have COOH, which is the functional group of carboxylic acids, and then finally, you have these two, so just copy them. Diol, they have two OH groups. Dicarboxylic acids, they have two COOH groups. Diamines, they have two NH2 groups. Dicarboxylic acid, again, they have two COOH groups. So we'll see how they interact in the formation of condensation polymer. But let me start by introducing you to, or I should say, remind you of the condensation reaction between carboxylic acid and alcohol. So we call esterification. Right, and we call what esterification is. Esterification is the combination of a carboxylic acid and an alcohol forming what in the process? Forming ester, right? In the process, remember? So when they combine, you will have something that looks like this. So you have RCOO, RC double bond O, and then you have an O alkyne, and this is the new bond formed in between. Yeah, this is the new bond, the line in purple. Okay, this is new. And then there's H2O formed at the end of the reaction. So you have H2O. Because the small molecule of water is taken out, this forward reaction is called condensation reaction. So can you put down the forward reaction? Does anyone remember the backward reaction? What is the backward reaction called? We can do the backward reaction by adding dilute HCl or dilute alkali. It starts with the H. Hydrolysis. Yes, I hear the word hydrolysis. So put that down. Why do we call the forward reaction condensation? Like we did in here when we named condensation polymer. That's because when we join the carboxylic acid and the alcohol, we have taken out a water molecule. You see, this is the part taken out. So we call this condensation. Now we just have to use the same concept, okay, to understand how is polyester formed. So how is polyester formed? Well, polyester, they don't just have one COOH and one OH group. They have two. So you can draw something like this, draw block. And then help me draw two COOH on the side. This is what a dicarboxylic acid looks like. It really just have two COOH groups sticking out at both ends. And then we have a diol. So for diol, you can draw them like candies. Okay, just like candy with two ends. Except at this time, the two ends, they are OH instead of COH. What happens if I join these two molecules together? Well, as you expected, we will eliminate the water from the end of the molecule here. But to your surprise, we don't just eliminate this H2O once. We remove it many, many times. And imagine having multiple copies of these, I'll assume it, don't worry. Imagine having multiple copies of the dicarboxylic acid and the diol. What will happen? We'll be able to eliminate water many, many times, right? We remove it here, we remove it here, here, and here. This process can go on as long as you provide more of the diol and dicarboxylic acid at the end. Okay? Yeah, so you can refer back to the video later. We have just started the discussion on condensation polymer. So We can do this repeatedly, and at the end, can you draw out the section of the polymer that gets formed? What do you think will be formed at the end? Well, let's start here. We will have something that looks like this, C-double-bond-O, and then you have the rectangular thing, and then you have C-double-bond-O, and then you have the new bond, right? Yeah, which connects it to the, is it the O or the H? To the O, yeah, because this H is now gone. When this is gone, you just draw a bond sticking the two together, okay? Like sticking the CO to the O. This is how you draw it. This is how you draw this purple bond. And then you continue. You have this circle thing, and the O, and you draw the new bond again. But we don't have to do this repeatedly. Why is that? This is because right after this blue O, what do you draw? You draw the, is it the red thing or the blue thing after the blue O? The red C-double-bond-O, right? And do you notice something? When you draw the C-double-bond, it's already a repeat of what you're seeing here. This is why there's really no need to draw the entire structure. It's just a waste of time. You can just draw the repeating unit out. So this is what we call the repeating unit. And it is at this point that I want to remind you all the difference between a repeating unit and a polymer. So when asked to draw the polymer, what do you show? You show everything, including the end. Including the end, maybe this is not clear enough. Let me also include the end, you see. This is the structure of the polymer. You include the green subscript N. But when asked to draw the repeating unit, you be careful, okay? You only draw the bracket without the N. You don't show the N. That's what we mean by the repeating unit. So to put it simply, they are basically the same thing. Okay, one has an N, one does not. That's it. Okay, so this excludes the N. So excludes the N. Okay, so that's difference between them. And what do we call this? We call this a polyester. Why? Do you see the ester group just one time or multiple times? Multiple times. That's what the word poly means. Okay. So right now, why is this called polyester? Okay. So why is this? By this, I mean this thing here. So why is this thing called polyester? For two reasons. Number one, it has the word poly because the COO bond appears many times. So many times that you lost count. Okay, so many times. Yeah. The second thing you notice here is why is it ester? Because it's not any functional group that repeats itself. Why don't we call it polyethylene? Well, that's because it's not the alkene bond that is repeating, but the ester bond. So it is the COO group. So this is called the ester group. It repeated itself many times. So you can understand this literally. Poly means many. Ester means, of course, the ester bond. Okay, the ester group. So that's polyester. In fact, polyamides, they are formed in a very similar way. Okay, so can you put down the key in here? What does this mean? This is a dicarboxylic acid. So dicarboxylic acid. And this is diol. So you will need two types of monomers in order to make polyester, as opposed to what you learn in Form 5. Remember polyalkene? Polyalkene needs just one type of monomer, the alkene, right? You don't need a different flavor of the alkene to make one long chain polyalkene. But polyester, not so much. You need two types of monomers. Each you will need many of, okay, in order to form the polyester. Now, before we do a summary on polyester and polyamide, let me also show you how is polyamide formed. So the recipe for making a polyester, as you saw, is many dicarboxylic acid and many diols. For making a polyamide, you will use one of the same ingredient. It is polycarboxylic acid. But the other ingredient, you have to switch it. Okay, you have to switch it into, so to show you that it is a different type of ingredient, let me draw a different shape. Okay, like a diamond shape here. So it is a diamine. Diamine has sticking out at both ends. And can you imagine what I can remove between these two molecules? What can I remove here? Also, OH and H. When we remove the OH and H, we can condense them to form water, right? So I want you to draw this maybe two of each molecule here. Show the two molecules, two of each molecule side by side. And then you can see that I can eliminate water from here, another water from here, yet another water from here. So now, let me give you all a task. Can you show me the repeating unit? Okay, yeah, perhaps now you will have a question. Why did I not start with HO when I first drew the repeating unit, right? Maybe that's what you're thinking. Why did I start from the CO double bond here? Why did I skip the OH group? That's because potentially, to the left of this title says there could be another diol, right? I could copy this and stick it over here. Then there will be an H from a diol to condense with the OH group, right? Which means we don't have to really show the OH group on this end of the molecule. You see I did not include this OH here. Because it can potentially condense with another H from a diol which I did not draw. Okay, so this is why you start from the CO double bond when you draw the repeating unit. Same thing here. So we will not show this OH group because potentially it can react with another diamine that's placed in here. But because I did not draw it, you don't have to show it. Okay, so can you start from the CO double bond and show me the repeating unit? Okay, here. Right, so what's the repeating unit like? Okay, so you have like maybe 20 seconds to 30 seconds to draw it. And then you can copy this structure first, but then the repeating unit I need to draw it. And then you can look up to check the answer. Right. Okay, so let's check the answer together. Do you get this? Okay, yeah. So make sure you do not show this OH group here. And I know you won't be confused when you do revision later, so you can highlight it in yellow. And yeah, and write down the notes on the side. So these two OH group we do not show. Okay? So we do not show this. No need to show the OH and H at the end of the chain. Yeah, at the end of the chain because they will potentially form water anyway. Yeah, so by potentially forming water is imagine that because you can have many of these molecules, and this is just a slice of what you're seeing. There could be more than just 1, 2, 3, 4 molecules, right? There could be 1,000 of these molecules lining up straight. And what you will see is that when you have another green molecule on the left, then this green molecule's H will be able to condense with the OH. So it will disappear anyway. So yeah, this is why you don't have to show this OH group in here. For the same reason why you don't have to show that OH group in here. Okay? Right. So now, don't forget to put down water as the other product. So you have many water in here, and you will also have many water molecules in here. Because in this process you are eliminating many H2Os, right? So you can highlight this H2O in yellow. So these are the H2O in yellow, right? Now, on the next page, we will look at some examples of polyester and polyamide. Okay, so starting with, so maybe some of you have seen the like this type of water bottle before, the Bon Aqua water bottle. Oh yes, okay, yeah, you can check the underside of the bottle. You will find this word.
Underside.
PET, yeah, either on the underside or on the packaging. So maybe at the bottom. Yeah, there's PET. So what does PET stand for? What type of polyester? Polyethylene terephthalate.
I'm just gonna call it PET.
Okay. Terephthalate. Okay, that's where the P, E, and T come from. So P, E, and T. PET. Yes. Okay. Yeah, you can call it PET, of course. But this is an example right now.
You don't have to spell it.
You don't have to spell it. But you do need to know that PET is an example of polyester. Why? They will show you the monomers, okay, the ingredients for making this type of plastic bottle. And by the way, you don't just find PET in bottles. Tonight when you send your clothes to the laundry, just when you put it in the washing machine, before you put it in, look at the label. You'll find a label that says 80% polyester, 20% cotton. Yeah. So some shirts will be made of 100% cotton. Okay, they are more capable of absorbing sweat. But more popular fiber for making shirt nowadays is the polyester. Okay, yeah. So this is to say your clothes are made of plastic. The bottles are made of plastic. You know, technically we can recycle the fiber in clothing and turn it into plastic. You know, Nike has a program. You know, the sneaker brand. They collect plastics from the ocean, and you know what they do? They weave it into fiber to make a sneaker out of it. You can check that out. It's Nike sneaker. Yeah. So you can do something for a good cause. Okay, if you buy those sneakers made from ocean plastic waste. Okay. Yeah. So just to say, okay. So now you know shirts and bottles. Write down 2 examples of articles, plastic articles. You have shirts. You have bottles. They are both made from PET, okay, which is an example of polyester. Now, what I will show you are the ingredients, so the monomers for making PET, and then you will need to use the structure to draw out the repeating unit. Okay, so this is the first monomer. You may be asked to classify it, okay, just by looking at the type of functional group. What do you classify this compound as? Is it an aldehyde? Is it a ketone? Is it an ester? Is it a carboxylic acid? Is it an alcohol? Carboxylic acid. Carboxylic acid, definitely. So you see a carboxyl group at the end. And the other important raw material is, can you name this compound? So you don't have to name this compound on the left, so I will name it for you. So close. Ethane 1,2 diol. Okay, so ethane. Yeah, you're just missing this part. Okay, other than that, it's mostly fine. Ethane 1,2 diol with an E. So there's an E here. What about this one? This one you don't have to know how we name it. Okay, it's terephthalic acid. Okay, so terephthalic acid. Okay, you just have to know that it is a dicarboxylic acid. That's it. Okay, and it will most likely be giving you these structures and ask you to draw the polymer. So let's start. How do we draw the repeating unit? What do we take out? We take out the H2O. Yeah, remember when you take out the H2O, you remove the OH from the carboxyl group. So remove the OH from the carboxylic acid. And then you remove the H from the alcohol. Yeah, so remove the H from the OH group. And this will form the water. Yes, so this will form water. These are what eventually forms H2O. So you will get H2O. So now let's do this. We have OH and H here. What can we take out from here? We can also take out the OH. And we can also take out the H from there. Okay, so can you draw out what is left? Can you draw out what is left? And that will be your repeating unit. Right. So, okay, let's check the answer. We will remove the OH this group, and then we have the H2O come on. So we replace it with a bond. So this is the repeat unit, okay, repeating unit of PET. Don't forget the N here. So the whole thing is PET. Yeah, you don't have to copy that name again, but just call it PET. We have removed a lot of water in the process. Yeah, we have removed a lot of water in the process. So that's PET. Okay, yeah, just need to know that polyester has this important feature. Then there's another also very important plastics, but you may not know that you have used it before. It's called Kevlar. Have you all heard of Kevlar?
No.
No. Do you know bulletproof vest?
Yes.
Bulletproof vest.
Yes.
Yeah. Usually you don't need to wear them unless you are working for a police or something. Yeah. So the bulletproof vest is made of Kevlar. It is another example of polyester. So in exam, yeah. So refer to the video later. In exam, you will be given the monomers. Okay, and now I'm giving you the monomers. I'll show you the structure in an app in a moment. So can you put down Kevlar? So the guy who invented Kevlar has just passed away not long ago. Okay, yeah, but he made important contribution to the scientific community because this can be used to make bulletproof vests. So just put this down. So normally you don't need to use it. Bulletproof vest. I hope you don't. Okay. So so this is. Okay. Yeah. So bulletproof vest. You can imagine that this is a very tough fiber for it to be used in bulletproof vest. I mean, you can even block bullets. Think about it. It's very tough. Okay. So what are the monomers? So draw them. We have COOH. You'll find that it has one of the monomers just like that of PET, but the other polymer, the other monomer is different. So it looks like this. Okay. So you have so OH in here and OH in here. So this is Kevlar. Okay, so this is Kevlar. So you can draw me the resultant molecule. Yeah, so draw me the resultant molecule. For what happens when we connect these two together. Okay. Oh, maybe can you change this to NH2? Sorry. This means this is an amide, a polyamide. Yeah, sorry. This is a polyamide. Can you fix that like that? This is a polyamide. So we have benzene, 1,4-dicarboxylic acid or terephthalic acid again. And on the right, we have benzene, 1,4-diamine. Yeah, so you don't need to worry about the name. What you need to worry about is the structure. Can you draw me the structure of the polymer, of what happens when we condense it? So you can copy over this rule here. We just have to change one word in here. It's to change the OH into NH2. So we remove an H from the NH2. Note that NH2 has two H's. You only remove one of them. You only need to remove one of the H's. You don't remove both of the H's, remember. So remove one H from the NH2 group. And together, it forms water. So let me show you how this works with one of the group here first. So the OH and the H, they eliminate. Okay, so can you draw me the product? You know we can keep most of the structure. We just have to take this part out and then connect them with a bond. Okay, at the ends, in the middle, and another end. And don't forget a bracket and N. Yes, and most important of all, don't forget to put also H2O. You have to put H2O there. You have to. Yeah, because condensation, polymerization always remove H2O. So can you put down N times this monomer plus N times this monomer together will form 2N H2O. Why would they form 2N H2O when you have N of these and N of these? Now let me ask you. If you just forget about this monomer for a second, how many water can I get from this OH and this H? So this OH and this H will form one water, right?
Yeah.
And this OH and this H will form another water, right? So if you have N of each, it means you have 2N water resulting at the end. You have double the amount. Because this part will form one water, this part will form another water. So therefore they are already two water formed for every one of these and one of this. Now multiply by n times. 2 times n will be 2n. So that's how you get 2n here. Okay, so write this up. So you have 2n H2O. Yeah, you can write it besides here. Okay, but if you think it's too distracting, you can write it here. Okay, so I'll put this in here as well. Write down n times this, n times that. Yeah, you have this. Yeah, this is Kevlar. It has so strong, okay, and intermolecular force that it can block bullet. Okay, let me show you the structure. So we have the molecule out here. So this is the we have Kevlar. Right. So this is Kevlar. You can see those hexagonal rings here, which represent benzene ring. If we turn it back into 2D structure, you can see the thing we just drew. So this is, oh, I don't know why it's so small, but you can see the Kevlar monomer here. So this is what the Kevlar monomer is like. So you have the benzene ring, the NH group, right? And then the C double O. So can you tell me if this is a unsubstituted amide or is N-substituted amide? N-substituted amide. Because you can see that the N here is connected to a carbon, right? A carbon. So this is an N-substituted amide. If both of these groups are hydrogen, this will be unsubstituted amide. Okay? So are we clear?
Yep.
Why this is like Kevlar? Okay, very important. You may look it up later. And this is a section of the fiber you take from a bulletproof vest. A bulletproof vest has millions of these lined up next to one another. So this will give it incredible strength. Okay? Right. That's Kevlar. The third and the last polymer I want to discuss with you, you have definitely seen this or heard of this before, is nylon. Okay, so nylon. So nylon, or nylon 6.6. Okay, I'll show you. This is not the pH value. Okay, yeah, but you can write down nylon where it is used. It is used in the making of parachute. I mean, if you are paragliding, the last thing you want to see happening is the parachute breaking in half. So nylon is a very tough fiber for making, these very, heavy duty stuff. So can you put down some examples? So parachutes. Ropes, if you're climbing, so they can be used to form very, very tough ropes. They can also be used to form the tennis racket strings. Okay, so this is like the tennis racket. You have these tennis racket strings. Okay, so tennis racket string. What do these three things have in common? They need to be tough. Okay, they don't break easily. I mean, if they break easily, you die. Okay, like parachute and ropes. Okay, these are bad. Oh, maybe you don't die and maybe break in half. But yeah, these two very important. Okay, so they all have to be tough. Okay, and strong. Yes, strong. So now we will look at the name nylon. Okay, what is an example? What is nylon an example of? It is an example of a polyamide. So of polyamide. Right. So we will look at the monomers again. I will draw you the monomers, and in the exam, you don't have to memorize the shape of the monomer, but when given them, you need to draw it. You need to draw the polymer, I mean. So draw it for me now. So you have CH2, 6, COOH, CH2, 4 COOH, and then soon you will know why it's called nylon 6.6. Okay. The other monomers that I want you to draw is CH2 bracket 6 and H2. So NH2. Note that sometimes in exam they will try to hide these functional groups from you. How? Okay, they will show you this. They will show you C2H4CO2H. They show you something ugly like this. You don't even recognize this, right? When I write CO2H. Well, this is actually COOH. Okay, just write this down. I don't mean that you need to remember both, but when you see this, it mean the same thing. Okay, yeah, or trick question. And this one here, the exam question can also simplify it as NH2, and then you have CH2 NH2. Again, they are trying to hide the fact that there are two H's sticking out from N. Yeah, but when you say NH2, a lot of students think that NH2 means this. This is of course a wrong structure, because H cannot form two bonds. Okay, so when you see NH2, it actually means two H's are connected one by one to the end. Okay, so don't make this silly mistake. Okay, when they write this, some student I see they will write this out. They think that this is what is happening. No, this is not. Okay, so you have this. Now I'll give you all 20 seconds. Again, you help me draw the structure while I name them for you. So I want you to draw the polymer. Okay, after I eliminate the water from them. Okay, so show me where the waters are eliminated, and I will ask you about the name. You actually know the name of these two monomers already in our AMAC discussion. What do you call a dicarboxylic acid? Yeah, you can figure out this, the polymer first. I don't want to overwhelm you with details. Okay, just draw the polymers and we'll name them. Remember, we should ignore this OH group because this OH group can react with an H from another amine to form water. So this is gone. And then we take another OH and H from here, we remove them as water, and then another H here will also be removed. You can say this H and this OH they combine to form water. And this H and that OH also combine to form water. So that means they are both gone. And in your structure, you shouldn't show the OH or the H. Okay, what do we have in between? Is this an amide or is this an ester? This is an amide, yes, because we have the con, right? You see con, so this is the con. And then you just draw two lines here. Is that clear? Okay. If you later when you review the pages, I want you to compare these three. They are actually very similar. Okay, if not identical. Okay, we are always doing three things. Number one, we put a bond in between where the water is eliminated. Number two, we add another bond on the left hand side and another bond on the right hand side, and finally we draw a bracket in. That's what we do. Okay. So now we draw the bracket and then N, and don't forget to add H2O, please. So plus H2O. So plus the water that you eliminated. Now the name. What is the name of this compound? How many carbon are there in total?
6.
What is the root for 6? Hex. So any take on the name? Very close. Hexane dioic acid. Okay, so hexane dioic acid. When you name a 6 carbon acid, let me draw it for you. Okay, 1, 2, 3, 4, 5, 6. What do you call a 6 carbon carboxylic acid with just one COOH group? Hexanoic acid. If you see a carboxylic acid with both ends being COOH, what's the difference? So write it down if you forget about this already. This is hexanoic acid. There's no E in here. So no E. But then when you see 2 carboxylic acid, you need to put back an E. And then you need to change it to hexane dioic acid. Is that clear? Okay, yeah, just put this on the side if this is unfamiliar for you. So you have hexanoic acid and hexane dioic acid if you see 2 COOH groups. Okay? Now, what about this guy? This should be easy. How many carbons do you see again? 6. So hexane 1,6 diamine. Okay, yeah, diamine, right? So we need 1,6 now. Why do we not need 1,6 here? That's because where can COOH group always be found? At the end. Can you find a COOH group anywhere along the chain? Never. So this is why the number 1 and 6, I took it off. We don't need it. It's redundant. So but here we do need them. So these are the names. You need to know it. You cannot know the structure, but you have to know how to name this compound from the structure. You can, yeah, okay? Now, we can look at, why is it called 9066, do you know? That's because to the
Hexanes.
no. Yeah, the 6 is related to hexane. You got it. Okay, but can you see that if we use this amide bond as a reference point, how many carbon are to the left of this dotted line in total? 6. How many are to the right? 6. Now you know where the two numbers 6.6 come from. So can you write down nylon 6.6? The first 6 means that in here there are 6 carbon. The second 6 tells you that, well, in the second half of the molecule there are 6 carbon. Yeah, and maybe you're thinking, are there other nylons with other numbers? Well, yes, there's nylon 6.10 and there's nylon 5.5, which would have different types of, property, okay, and we don't need to know that. We are not expert in material. We don't need to know the uses of each and every type of nylon. Just know that nylon, just like steel, there are many types of steel, right? There are some steels that are, tougher than the other. There are also some nylon that are tougher than the other. But we just need to know nylon 6.6 in the SE. Okay? Right. So that concludes the important organic molecule chapter. What have you learned in this chapter? You learned about soap, the making of soap. There are two types of detergent, soapy detergent and soapless detergent. Soapy detergent are made from fat and oil. Soapless detergent are made from petroleum. Okay? We also learned about aspirin, okay, the painkiller, which has what other properties?
Blood thinning.
Yeah, blood thinning. What if you are feeling fever, having a fever? It can also have antipyretic property, meaning it fights fever. It can also, but then aspirin should not be taken with alcohol. Yeah, this I forgot to mention. Can you put this down? If you are an alcoholic, then you may not want to take aspirin. Okay, because write this down. I forgot, but now I remember. Aspirin must not be taken with alcohol. Why? Well, you can try and learn it the hard way. Okay, you will have stomach bleeding. Stomach bleeding. Okay, so it must not be taken with alcohol, or it will cause stomach bleeding. Okay, right. I don't think I need to tell you that there are certain drugs that must not be taken together. Okay, there are drugs that would act in a way that would cause some side effects. Okay, and therefore should not be taken together. In this chapter in chemistry, we learn one such drug combo is aspirin and alcohol. You don't want them to come together. Okay, so when they come together, you get stomach bleeding. Okay, so but I trust that they say you shouldn't be drinking. Okay, so yeah, right. So now we are finally in the last core chapter. Yeah, you can finish copying that first. Okay. Yeah, so we can start a bit on the last core chapter, and then we'll move on to electives. Okay, so we're making some progress. Okay, so the last part in core, okay, is the trends in the periodic table. Yeah, new book. I think it's chapter. I don't remember the exact number.
Is that goes with the polyester?
We are just done with, just a moment. Yeah, we are just done with book. I don't know what book this is, but we're just done with 11, topic 11. Chemistry of carbon compounds.
So is that related to?
It's, you mean this chapter?
Does it periodic something like that?
Oh, yeah, the periodic trend. This is exactly chapter 47.
Oh, so it's a new chapter. Okay.
Yeah, it's a new chapter. Yeah, it's not related to what we discussed just now. It's a new one. Okay, new one. You might want to start a completely new page.
Yes.
So it's patterns in the chemical world, where we look at the trends in periodic table. So the periodic table does more than just recording elements for you. Okay, it shows you property. I like to look at it as like a giant cheat sheet. Okay, it shows you a lot of properties, useful properties. For example, on the left, where do we find the metals? Can you tell me? Do we find metals on the left or on the right? On the left. We find semi-metals in between. We find non-metals on the far right. Yeah, so you don't have to draw this table, but you can just draw like an arrow here saying, well, on the left we have the metals. In between we have the semi-metals, and semi-metals are also known as metalloids, okay, aka metalloids. Okay, you may see this word in exam. Just treat it as the same thing as semi-metals. Then on the far right, we have the non-metals. So the non-metals are here, which extends all the way to the noble gases, of course. So you have the semi-metals. Yeah. What does it mean to be a metal? Can you think of some properties of a metal?
Strong.
They are hard. I may not agree when you say it's hard, okay, because they are only shiny. Yeah, so that's almost always true. Are they conductor or they insulator? Conductor. But whether it's hard, I might have to disagree with some metals. Okay, they're pretty soft. What about mercury? Would you say that it's hard? No. Yeah. No. Okay. So can you put down some properties of metals? They are always right. Shiny. Good conductor. There's not a counter example that I can think of, okay, when we say metal is a good conductor. Even mercury is a good conductor, okay? And even mercury is shiny, okay? For semi-metals, okay, they are usually shiny. So usually shiny. And you will start to know why they are called semi-metal, because they have like a mix of properties of both metals and non-metals. Therefore the name is quite a fitting name. The second is the most important property of semi-metals. They have low conductivity at low temperature. But then at high temperature, they have high conductivity. So that means their conductivity changes with temperature. But for metals, they are good conductor no matter what. Okay, whether it is hot or cold, it's good conductor. Semi-metal, they have some kind of selectivity. So they have high conductivity at higher temperatures. So non-metal, we say, they are usually dull-looking. So I said usually because I have a counter example. It's diamond. I don't think we'll say that diamond is a dull-looking substance. Okay, diamond is pretty attractive, right? It's pretty shiny. It's pretty shiny. But of course, it's a different type of shiny. Yeah, than metals, right? But then you have to know that they are usually insulator. Right, so can you put down a major exception here to the fact that they are usually dull-looking? So except diamond. Diamond is certainly not dull-looking. And what about another non-metal that you can think of that serves as an exception to this rule that says graphite? Yes, except graphite, right? So yeah, that's graphite is not a gas. Graphite is gallium. Gallium is a metal with a melting point below that of 37 degrees. So this is why, at room temperature it's a solid. But as soon as you put it at the palm of your hand, it melts into a liquid. Yet you can play with it as if it's a liquid. But as soon as you let go of it, as soon as you let go of the gallium and it liquid comes to the table, it will solidify back into a solid. So it's quite strange, the metal. But mercury is a liquid, okay, at room temperature. So we have metals, non-metals, and semi-metal. And then, metal, non-metal, and semi-metal, right? Then we look at the bonding character. Okay, so here you can put down the first property, the first trend that we look at is the metallic versus non-metallic character. So metallic versus non-metallic character. The first kind of trend we notice as we go across the periodic table. The second trend that we will see as we move across the periodic table is the bonding and structure trend. So bonding and structure trend. So when we go from sodium to, so I want you to write down a few selected metals here. NaMg, we have AlSi, PsCl, and then Al. So I want you to write down the name in bonding in here, starting with, so if you don't have enough space to fit that away, you can write it on a separate line. So you have Si, PsCl, and Al. We have some metals on the left, some semi-metals in the middle, and then some non-metals on the right. So you know these are the metals, Metals, of course, have what kind of bond?
Metallic.
Metallic bond. Oh, I can't think of another bond that metals have. Okay, other than this one, it's quite obvious, you see. Semi-metals and non-metals, they have covalent bonds. But then, you see the last one, argon, the last element, argon. I did not include it in the discussion, okay, with PS and Cl. Why? Because to which group does argon belong to? Noble gas. What does noble gas form? Do they form bond? No. So this is why the discussion on bonding doesn't apply to argon. Okay, just put down no bond because it's already stable. If you're already stable, you don't have to bond because bonding is a means for you to gain stability. Okay, so already stable, so no need to bond. What about for the others? So we have metals. So just write down metals form. Metals form metallic bond, of course. Right, metals form metallic bond. Semi-metal forms. So semi-metals form covalent bond. Yeah, so form covalent bond. Even non-metals form covalent bonds. So at this point, you will ask me, so what's the difference between semi-metal and non-metal then if they form covalent bond? Well, it's not the bond that they form that differs. It is the structure that they form that differ. So can you help me create another row in here? The first row is a discussion on the bonding characteristic. We will now look at the structure characteristic. So you know structure, maybe you can create a small table on the side. There are 3 types of bond in DSE chemistry, or in any chemistry for that matter. And there are 3 types of structures. Okay, so let me put that down. Well, actually, there are 4 types of structures, sorry. So there are 3 types of bonds, but 4 types of structures. What are the 3 types of bonds? Let's do a quick review. Ionic bond. So put down ionic bond, covalent bond, and metallic bond. I can't think of the 4th type of bond unless you can. Those are structure. Yeah, those are structure. Yeah, so bond and structure we need to see.
What about van der Waals?
Van der Waals forces, it is not technically speaking a bond because it exists between molecules. It doesn't exist between atoms. Okay? Right. So 4 types of structures. So we have giant ionic, giant covalent, giant metallic, and simple covalent. So giant metallic, giant covalent, and simple covalent. Simple covalent structure are also known as simple molecular substances. Okay, so AKA simple molecular substances. And let me tell you how you can tell apart the giant from the simple substances. Giant substances, they always have high melting and boiling point. They are always solid. There is not a giant structure that you can find in chemistry or in everyday life that is a liquid. Yeah, so write down giant. What giant mean? Whenever you see the word giant, it must be a solid because it must have high melting point. So giant structures must have high melting and boiling point because of the extensiveness of the structure. So they must have high melting point. Therefore, they are solid at room temperature. Simple molecular substance, not so much. They are usually gases or liquid. Yeah, they usually have lower melting and boiling point. So simple structures have lower melting and boiling point. Yeah, so melting and boiling point. So therefore, they are usually liquids and or gases. But note that I said usually. There are exceptions though. Do you know what the state is for iodine at room temperature? Iodine is a solid. It's a solid, okay? Which is why I like to show students this video when I discuss iodine. So this is iodine. You can see that it's very clearly a solid. And when you apply heat through a heating filament onto it, what is the color of iodine gas?
What is that?
into this very beautiful purple gas.
Yeah,
This,
really.
Oh my god.
yeah, this is iodine gas. Yeah, I think now that you can see it, you will not forget about
Can
it.
you breathe it?
No, unless you want to go to the ICU, I guess. Yeah. This is toxic. All halogens are toxic. You know, chlorine was used as a weapon in World War One, right?
What?
Chlorine. Chlorine. The one you use
We
to
don't
fire
take
the
history.
people.
We don't take history, sir.
Well, now you do. Now you do. I don't study history, but at least I know. You should know. So all halogens are toxic. Yeah, if you want to breathe it in, well, if you want to go to the ICU, you can like take a deep breath. Okay, when you find them. All halogens are toxic. So can you put down? They are usually gases, except iodine, which is a black solid, which gives off purple flame. Okay. By the way, you need to remember the state change from solid to gas. What do you call the state change from solid to gas directly? So put this down. Yeah. No. It's not with S. It's sublimation. Okay. So put this down. We have this. You need to remember each and every of these arrows here, and I'm sure you know the remaining four. The remaining four you learned it in Form 1. Yeah. So can you tell me what is this? Solid to liquid. Melting. Liquid to solid? No. Freezing or solidification. Yes. So freeze or solidify. I think the term solidify is more, general. And gas to liquid. For those of us wearing glasses, you know, when you step out of a condensation, yeah, you see the glasses will be fogged up, right? It will fog up, okay? So this is condensation. What about liquid to gas? Evaporation or boiling. There is a tiny difference between evaporation and boiling though. Evaporation happens at all temperature. But boiling only happens at boiling point, at or above boiling point. So you see here, this is very important. Okay. Boiling happens only at boiling point, at or above. But evaporation happens at all temperature. Okay? Yeah, so it happens only at boiling point and what happens at room temperature, at boiling temperature. And finally, this is tricky, so I wanted to maybe highlight it. It is sublimation from solid to gas. SUBLIMATE, sublimate. When things sublimate, it turns from solid to gas. The reverse process is deposition.
What?
Deposition, deposit. There are two chemicals you must know in DSC that would undergo this state change. One is iodine. So only two chemicals in DSC does this. Okay, so only two chemicals in DSC changes from solid to gas directly. So changes between solid and gas directly. They are iodine. So I wanted to draw it. So this is iodine solid. It is black. So black, I2 solid. And as you saw in the video, it will turn into purple gas. Yeah, purple gas. So it turns into, this purple gas, which is I2G. So this is I2G. It's purple. Another substance you should know. When you buy takeaway at the ice cream store, what do you get?
Liquid nitrogen.
Oh, I'm pretty sure I get liquid nitrogen.
Dry ice.
You get dry ice. Liquid nitrogen is very expensive to maintain.
Dry ice.
Yeah, dry ice, but it's much cheaper. So dry ice is a white solid. Okay, so white. What is the chemical formula of dry ice? What is dry ice chemical formula? Carbon dioxide. It's carbon dioxide, dry ice. Yeah, so you have white CO2S. This is dry ice. Write this down if you don't know already. When you leave dry ice at room temperature, it will just sublimate. We don't say evaporate, because evaporation means it has to go through liquid state. It turns into a colorless gas, which is why you don't see anything here. So carbon dioxide is colorless. Okay, so it turns into colorless CO2G. So these two substances undergo state changes as shown. Okay? Right. So right. Now let me finish the structure here first. Okay, yeah. Can you create an extra row here? We just saw what kind of bonding there are among these molecules. Now we look at structures. So what kind of structure can be seen in metals? Apparently, which of these structures will you find in metals? Giant metallic. I mean, there's only one word that you can relate to metals, right? Yeah. So can you put down structures here? And under all the metals, write down giant metallic. Okay. So from this part to this part, you have giant metallic. So giant metallic structure. So silicon. Silicon is the only one that forms giant covalent structure. So semi-metals, they tend to form giant covalent structure. Okay, so you can put this down in here. And non-metals, non-metal, maybe the arrow shouldn't extend that far. Okay, so it will only be this part. Okay, up to, it's only Si that form giant covalent structure. Na to Al forms giant metallic structure. Okay, so you put down from Na to Al, giant metallic structure. For Si only, it forms giant covalent. But from P, okay, onward, P to Cl. So from P to Cl, they form, what do you think? Simple molecular. Okay, they cannot form giant ionic structure because what does an ionic compound contain? A metal and non-metal. Yeah, you don't see any metal on this part. You only see non-metals. So they form simple molecular structure, or I should say they have simple molecular structure. Okay, right. And on the side, I wanted to just draw like a very simple diagram describing each structure. What will you include in your drawing if you are asked to sketch what metallic bond look like? What do you see in a metallic? C of the localized electron. You also see which type of ion. Do you see positive ion or do you see negative ion? Positive. Why? Why not negative ion? Because metals only form positive ion. Have you seen any minus before? Have you seen Al3 minus? Never. Al3 plus instead, right? So can you draw a simple, they might give you a box in the exam, and have you draw what metallic bond looks like, okay? So, and then we will include two more diagrams here. So this is what the giant metallic looks like. So giant metallic, and this is giant covalent, and we have simple covalent. So for me, I like to look at giant covalent as like a single large, molecule. So a single large molecule with n atoms, with an uncountable number of atoms. Okay, so many students ask, how do I know which is a giant covalent structure, which is a simple covalent structure? Easy. Just check if there is a countable or an uncountable number of atoms. If you have an uncountable, yes. I mean, just think of diamond. Can you count how many atoms there are in diamond? Well, I would rather not to, okay, because it's a lot, okay, uncountable, so much so that. So uncountable number of atoms, underline the uncountable. Simple molecules, you will always find a countable number of atoms. Okay, you can put down, like CO2, I hear CO2. You can put down C in diamond. You can simply not count it because it's astronomical. Okay, to a point that it is uncountable. What about CO2? There is a countable number of atoms. Okay, like for example, there is 1 C and 2 O in CO2. I mean, you can actually tell me there is only 1 C and only 2 O in CO2. You can definitely count it. So therefore, draw out metallic structure. In giant metallic structure, you will need to show a lot of positive ion and a sea of the localized electrons. Try to show, if you have 6 positive ions, you should only show 6 electrons. Okay, if I am a very picky examiner, I will check to see if it's neutral. If I see a 7 electron here, when you draw 6 ions, maybe I'll mark it as wrong answer. Okay, you know some people like to pick on details. It has to be neutral.
So
It-
mean.
Well, then just show 6. Just show 6
Okay.
every time. Yeah, can you put down the localized sea of electrons? And this is what we call a lattice. Not like the vegetable, a lattice. A lattice means a regular arrangement. You see it's very tidy, right, the positive ions. They're not all over the place. They are at a certain location. We call this lattice. If you're unsure what this word means, it means regular arrangement. It's not a mass that you see in here. Well, maybe the electrons are a mass, but the ions are not. It is in a regular arrangement of cations. It has to be cations, not anions. Giant covalent structure. We will only draw graphite in here. Yeah, this is graphite. Diamond is a lot harder to draw, but you can see that diamond, like graphite has these hexagonal layers of carbons, and you will lose count, okay, of the number of carbons because there are many. You just can't count. There's just too many, and you can draw dotted line here to show that the structure still goes on. It doesn't stop. It extends in many directions, okay? It extends in the X direction, okay? That's giant covalent. Finally, we have simple covalent, okay? So simple covalent, we can draw things like P4 and S8. So this is S8. Yeah. Not many students knows the shape of S8, but many knows the shape of Cl2. What does it look like to you? What does this look like to you?
A crown.
It looks like a crown. So S8 is crown shape, okay? So we have S8. So this is a S8 molecule. You can see that there are exactly 8 sulfur. You can count it, right? You can count 8 sulfur, which is why it belongs to a simple covalent structure, not giant covalent. Because in here, you have N carbons. That's why it is giant. Yeah, N. So you have N carbon. Why is it simple on the right? That's because you have 8 sulfur. No more, no fewer, but 8. So you have 8 sulfur. 8 is a countable number. N is an uncountable number. Okay? So is that clear, the difference? Right, so we'll pick up from here tomorrow. Okay? So, any questions?
No.
No, okay, so we are in the last stretch of this part, okay? So let me upload this onto Google Classroom.